So welcome everybody to the webinar on the Python integration toolkit for LabVIEW. My name is Andrew Collette. I'm a scientific software developer here at Enthought, and I'm joined today by my colleagues Jim Corson and Courtney Gottschall, who will be handling the questions. So to give you guys an overview of how this is going to work, we're going to spend a little time in the beginning here on what the toolkit is, who Enthought is, why we thought this was a good idea, how the toolkit works. And then we're going to jump straight into some live demos. I think the best way for you guys to see how this thing works is just to show it to you. And so we're going to start with a Hello World demo. I'm actually going to go through and build live Hello World using the toolkit. Then we're going to talk about how the toolkit can help you accomplish some tasks in LabVIEW, including signal processing and machine vision image processing. We're going to finish up the live demo session with an example of how you can use the toolkit Lab Python to talk to cloud services. And then finally, we're going to show you guys a preview of a very exciting feature, an upcoming feature in the toolkit, which is being able to use it with Application Builder, which means that you can use the LabVIEW facilities for bundling your application into a standalone program and bring along Python and all the tools and so forth for that. And finally, we'll have you a slide up to tell you how to get your hands on the toolkit, and we'll have a few minutes for Q&A at the end. So a few administrative things up here at the front. We're going to be responding to questions live. There is a questions box in the GoToWebinar control panel, so please ask any questions there. And everybody who are, of course, will get a recording when it is over. Great. So it's worth taking a few minutes at the top here to talk about who we are and kind of the perspective that we bring to this. So Enthought has been involved in scientific Python for many years now. I think it's over 15 years since the company was founded. And we were originally a consulting company. We now do a mixture of consulting and product development and training, all focused around the Python platform. We got our own Python distribution, which I'll talk about in a minute, with many users worldwide. And we're coming to you live here today from Austin, Texas. We have additional offices in Europe and in India. So Enthought's perspective, for using Python is really about helping people solve real-world problems. So we are a software company, of course, but the software is a means to an end. I come from a scientific background, and most of the folks here at Enthought do as well. And we're used to trying to get things fixed in the lab and trying to do science, trying to do research, and moving forward. And we use Python to do that. So we have a number of tools at our disposal that we use to do that, one of which is a complete Python environment we make called Enthought Canopy. That includes Python, plus facilities for installing packages, plus the full IDE, development environment, debugger, data import tools, and so forth. And our approach to solving problems with Python really is highlighting the nature of Python that makes it very friendly for using packages. And so Python is a very extensible language. And of course, there are many open source packages for it. And we build on that and use a combination of open source Python packages and domain-specific stuff that we can use to solve problems in particular domains. So a few words about Python. So of course, Python is a high-level language. It's interesting, actually. We spend most of our time, if you look at the applications that we write, the program spends most of its time actually in compiled code. And so you really have kind of a best of the both worlds situation. You have a high-level language that's very flexible, very easy to develop, very easy to test. When you want to change your program down, a few months down the line, when you have a new great idea, it's very easy to go in and do that. And you can actually leverage these compiled libraries that do things like machine learning, like machine vision, signal processing, things that would have to happen in a compiled environment. And so Python is very useful as a high-level kind of glue language to tie these things together into a solution. We, of course, use Python in scientific and engineering domains, and we love it there. We are also embedded in a larger community. And so, of course, folks who are using Python are using it for all kinds of things. For example, scientists and engineers may not want to sit down on the weekend and write their own web server. And so we are able to take advantage of the efforts from the greater Python community and use those for our purposes. It's pretty shocking, over the last couple of years, last 5 years or so, that I've been around for seeing how Python has really broken into industry and is now being used in all kinds of places, including engineering and scientific applications, aerospace industry, automotive manufacturing, electronics, test and measurement is showing up everywhere because of these very friendly characteristics, very easy to develop and very easy when you have to talk to low-level functionality. And this this right here is kind of, the biggest thing out of all these wonderful things about Python. It's the fact that it's a very modular language, a very modular platform, very easy to do code reuse. That means your own code that you guys develop internally to solve your own problems, and also code that people have written and shared. And so it's one of the reasons that Enthought has been successful, and one of the reasons that my career as a scientist was successful, is being able to reuse the contributions of other folks. And that includes packages for doing array mathematics, signal processing, usual suspects over here. And so I put a couple of logos up to give you guys an idea of the huge array of packages that are available that you can just pick up and start using. So the other side of the coin here is LabVIEW. And so the image that you're seeing here on your screen is actually a picture in my old lab. My former career was as a laboratory research scientist. And this picture, the kind of stuff you see in this picture is pretty typical. This is an academic lab. But of course, if you're a small electronics lab, any kind of test and measurement environment or a manufacturing floor is going to have kind of a similar mixture of things. And so in this kind of an environment, it's all about talking to hardware. Right? There's probably over $1 million worth of equipment in this photograph. And that hardware talks to machinery, it acquires data, it talks to other hardware in other buildings. And the interesting thing about it is that everything in this picture relies on software to get its job done, right? I mean, you can't have digitizers and so forth need to be attached to a software platform to be coordinated, to take data, and to communicate with the scientists. And in particular, this laboratory and many others run on LabVIEW. And LabVIEW is this platform made by National Instruments, which is a company here in Austin, Texas. And the great thing about LabVIEW is that it makes it very, very easy to talk to hardware in the lab. Not only talking to hardware, but also being able to provide a graphical user interface. LabVIEW is a very dynamic environment, so it's very easy to build a custom user interface for a machine or a data acquisition platform or a motorized thing or whatever you have in mind. And because it's very flexible, you can actually build programs in it if you're not a professional programmer. And that means that people in the lab who just want to get their work done, like scientists and engineers and technicians and grad students and postdocs and so forth, can use LabVIEW to do some pretty sophisticated things that otherwise would need dedicated programmers who are skilled in operating embedded equipment. And so the combination of these three things leads to basically to an environment where it's possible to do very rapid iteration. And so in academic laboratories, of course, things are changing very quickly, and in industry and manufacturing, people are generally on a timetable, and we can't stop everything and take a month to rewrite the software. And so LabVIEW is a tremendous platform for that. And we'll show you LabVIEW in a little bit here if you haven't seen it before. So we look at this situation. We have Python, which is used for doing data analysis, being able to leverage this wonderful open source ecosystem. And we see LabVIEW, which is this great environment for talking to hardware and developing ad hoc interfaces. And so the question that we ask, what is the best way to use Python and LabVIEW together to solve problems? And what's interesting is, from a technical standpoint, there are really a number of ways you could do this. You could imagine making a custom version of Python, for example, that would be embedded in LabVIEW. So it would have, a set of packages that you thought was interesting for other users to use, and you'd be limited to that. So we looked at this problem, we thought about it for quite a while, and the more we thought about it, the more we realized that, Python is a wonderful ecosystem and environment all on its own. You've got all these packages out there, you've got an established tool chain for developing software, for deploying software. You've got, development environment, debugger, all this great stuff that is already there and in place. And on the other side, you have LabVIEW, and LabVIEW, is its own beautiful ecosystem, complete platform, already integrates with hardware. And so it's less about, trying to combine these two things and more about trying to build a bridge between them. And so that's the idea behind the Python integration toolkit for LabVIEW. It is an add-on for LabVIEW that allows you to communicate live between a running LabVIEW process and a running Python process. It takes care of all the boring stuff like setting up the communication and handling the vision, all that kind of stuff. And all you have to do is put a little bit of code in your LabVIEW program, and now you can talk and exchange information seamlessly with Python. So if you imagine this as a bridge, there's kind of two sides to the bridge, and we'll start with the Python end. So the Python side basically starts around, it's designed around a module, a Python script, if you will. And this script does not need to know about anything in LabVIEW. It can be an ordinary Python program. It could have been developed externally, to do something else. And you can develop it with, like I said, with the full suite of native Python tools like an IDE, like a debugger, and of course you've got facilities to install packages into Python using the standard machinery for that, which means you can take advantage immediately of all this great software out there. And so basically you write a Python module with some functions in it, with some variables in it that you want to access from LabVIEW. And then on the LabVIEW side of the bridge, the Toolkit provides, it's an add-on that provides a series of LabVIEW functions. They're called sub-VIs. And these LabVIEW functions live on your block diagram, and they allow you to talk to Python. And so one of these, for example, is called new session, which you use to launch a Python session, and you point it at your module that you wrote. And now you've got access, live access, to all the functions in that module, and you can call them. You can call native Python functions. You can set and get variables on demand. And like I said before, it handles all the boring stuff. It handles all the conversion. It handles all the types. And so you don't need to do things, for example, like saving data to files on the file system to communicate between LabVIEW and Python. And that gives you kind of a very high-level overview of how this works. But what I really want to do now is show you guys a live demo, because it's easy to talk about this stuff, but really to nail it down, we have to show it to you. So what I'm going to do now, I'm going to zoom over to my Windows machine, and I'm going to show you guys from scratch how to do Hello World. So Hello World is kind of a standard programming thing when you're using a new environment or new language. It's a good demo to show, it just says hello, and it's a good way to see all the tools that are involved. And so we'll start with the Python side of the bridge. So I'm going to have, so of course you're welcome to use your own Python environment if you have one that you like. When you install the toolkit, you get along included with it a full copy of Enthought's Python distribution. We wanted people to be able to use Python out of the box when they install the toolkit. And so if you don't have Python already, you're welcome to use this or whatever you prefer. And so here's the Enthought Canopy environment. So Enthought Canopy is a Python distribution plus a development environment that you're seeing here, plus, of course, facilities for installing packages. And so I'm going to create a new Python module, create new file. And we're going to write the world's simplest Python program here. It's just a function that takes somebody's name and says hello to them, right? And so we'll do def say hello, and it'll take a name, and it will return a string here that says hello, and put their name. And we'll also have it print out a little bit of information here to the console, so we can see that it's doing something. This is a pretty simple function, but of course I want to test it. And so the great thing about Canopy is that you can write your code here, then you can test it on the fly. There is actually a live Python session running right here in Canopy. And so I'll run that. And now, this say hello function will be available for me to test. And so I can do say hello, and put my own name in there. So you can see it did two things. It printed some output to the console. And then, of course, the function returned a value, which is hello enter. So very simple, very easy to do, right? I'll save that, and I'll put it here on my desktop so we can find it. I'll just say hello. Hi. Great. And there it is. Okay, I'm going to minimize Canopy now. So our Python end of the bridge is finished, right? We've got our Python module here, which is this file on disk. It's got a little function in it. Of course, I can put as many functions as I want, but I'll have just one for now. And I'll minimize out of this. And now we'll zoom over to LabVIEW. And so for folks who may not have used LabVIEW before, LabVIEW is a 100% graphical programming environment, which is one of the reasons that it is so flexible and allows you to do rapid development. And so the center of the LabVIEW universe is something called a virtual instrument, which is basically a LabVIEW program. So here's a virtual instrument. And the first part of it you're going to see here is called the front panel. And this is a canvas on which you build your user interface. And you can put whatever you want here. There are palettes full of controls. You can have, list boxes and graphs and so forth, and buttons and numbers. And of course, we want to talk to our Python function, and so we just want some string inputs. And so over here, one of these palettes lets me put string inputs. And so here's a string control. This is a text box that I can put anything I want. I'm going to call it name. So it'll be how I put the user's name in. And then, of course, in addition to a control, is an indicator. You can think of this as kind of an output field, right? And so I'll put that over here, and I'll call it output. So my small LabVIEW program here is pretty much done as far as the front panel is concerned. I got an input field and an output field. And the other window that opened behind this over here is called the block diagram. And like I said, LabVIEW is a 100% graphical programming environment. And so you'll notice that there's two little terminals on this block diagram over here that correspond to the input and output fields on my front panel. And the way you make your LabVIEW program is you literally wire these together along with whatever functions you want to provide the logic of your program. So for example, a trivial program would be to take the input over here and literally just wire it to the output, right? And then if I put some text in the name field over here and I run the program, it'll take it from the input box and put it in the output box. Very simple. So let's see how we can use the toolkit to call Python and call that say hello function. So I'll get rid of the wire over here. Now when you install the toolkit, in addition to getting Canopy if you want it, you also get an add-on palette here. So in the same way that you can have this huge list of controls that you can put on the front panel of the VI, this is a list of functions or sub-VIs that you can put on your block diagram to do various things. And so the first one we're going to put down over here is called new session. This is a function that takes the path to your Python script and then launches Python in a separate process right alongside LabVIEW, so it's available to be called. And so there's a whole bunch of inputs that you can put over here. And so the first one we want is called the path to Python module. And I'll just create a constant over here, and I'll browse for the Python module we did. Browse for path on desktop. And here's the say hello module. All right. And so now, when this program runs, the new session sub-VI here is going to launch Python and point it at this module and make all the functions in that module available to us. So we're also going to need to call a function. So we're putting this node over here called call, right? And we're going to provide the name of our function, which I believe was say hello. So def say hello. So it's got an input for that, function or method name, say hello. And this LabVIEW function over here, the sub-VI, we'll call that function. And of course, I need to provide input, right? I need to provide the user's name. Somehow I'll take that name field and send it to Python so that we can have access to it in the function. And so the toolkit provides sub-VIs to do that. This is the one that you use to send information from LabVIEW to Python. It's called pack. And you can put whatever LabVIEW type you wanted to here. We support strings and booleans and floating point numbers and so forth, and arrays of all the above. So you wire that in. So be the argument. And if you've got multiple arguments to your function, you can put multiple copies of this, right? And we're going to wire all these things together so that the call function, for example, knows which Python session we're talking to. And we'll also wire up the error, and we'll wire in the data that we packed up to send to Python. And so our function prints some console output, and it also returns a string value. And so we want to get that data, that item back from Python and display it in LabVIEW. And so just like you have a pack VI here that takes your LabVIEW data and packs it to be sent to Python, we also have an unpack VI, right? And this is kind of the opposite side. This is the thing that you use when you've got a Python value coming back. This is the thing you call to turn that Python value back into a LabVIEW value. So we'll wire that up. And now it'll take the output from the Python function, and it will display on the front panel. And of course, when we're all finished here, we can choose to close the Python session. This will shut down Python, and that Python session will go away, and we'll just have LabVIEW running. So we'll wire that up. Great. And there's one more thing I'm going to do. By default, you may not want to have the Python console popping up all over the place when you're running these programs. And so by default, the Python console will be hidden. And so we're going to tell this thing to turn it on so that we can see the output. So show console. Great. All right. So it seems to be set. I'll put my name in over here, and we'll see what happens. We'll run it. So we got a Python window, and we got some output from our function. It's printed saying hello. And now, if we look at the front panel of the VI, here is the response from the Python function. And so this is the concept, right? You write your Python module, you have your variables and your functions available in that, and using the toolkit, you can pass data from LabVIEW to Python very simply, call a function, and then retrieve the result. And so the last thing I want to show you guys with this demo here, the Hello World demo, is actually pretty important. Like the workflow that I showed you guys is very straightforward as far as the type conversion is concerned. I send a string to LabVIEW very easily, and I retrieved it very easily. But of course, it's still kind of a batch mode of operation, right? You got some inputs, you got a Python function or a script that you call that produces some outputs, and then it's finished. The great thing about the Python toolkit here is that once you've created this session with new session, you don't need to immediately. You can keep that session around and call into it and access variable values again and again and again for as long as you want. And so one thing I'm going to do here, I'm going to move this out a little bit. In the center portion of the program, right, where we're sending the value from LabVIEW to Python and calling the function and retrieving the result, I'm going to put that in a loop. And so LabVIEW, of course, is a graphical programming language. And so you have not only these basic functions, but also loops. And so this is a while loop. It's going to go around and around and around until I tell it to stop. I'll create a stop button. And so what this is going to do is it's just going to continuously call, it's going to launch the Python session. The session is going to hang around, and we're going to call into it repeatedly. And every time we change the value of the name field over here, Python should display it, should run the function and produce a different output. And one little tweak I'm going to do over here, you'll notice that these controls in the LabVIEW front panel have a whole bunch of options over here. And you can change these to change the appearance and the behavior and so forth. And I'll set that to update the value so that LabVIEW will recognize the value change right away. And so I'll run that. And now, right, we're running Python as fast as we possibly can. It's hammering over here. If I change this, a different name, now I'm calling Python live and it's producing output live. And so this is an example of a pattern that's very common with the toolkit, where you start up a long-running Python session that's running alongside LabVIEW to do things like signal processing, number crunching, and so forth, that you want to happen in parallel while your main program is off doing something else. All right. So that's Hello World. And I'm going to zoom back over here to my slide deck. So Hello World gives you an idea for how you can use the basic functionality of the toolkit, what it means to pack data, unpack data, how to call functions. But of course, the data types that were involved with that were just strings. The Python function took a string and formatted it into another string and returned a string back. And one of the great things about LabVIEW is that it's very easy to deal with numerical data, with arrays of numbers. And so, of course, the Python integration toolkit also allows you to send and receive arrays of numbers between LabVIEW and Python. And so the example I'm going to show you guys now actually is an example that ships with the toolkit alongside a whole bunch of other examples that ship with the toolkit that show you how to use Python alongside LabVIEW to do some more sophisticated processing of images and also of signals. So, zoom back over here, and I will close out of my Hello World now. Don't save, I'll close the windows that I opened. And so I'm going to go over here to an examples directory. And so again, these are all the examples that ship with the toolkit that are available through the LabVIEW example finder. They're in vi.lib. They're installed right along with the toolkit. So the first one I want to show you guys is this one over here. And this shows kind of a typical pattern in the lab that I encountered quite a bit when I was a scientist, which is that you've got a LabVIEW program which is talking to hardware and acquiring some data, right? And in this case, we have some simulated data. What's happening is that kind of 1 second intervals here, we're acquiring data from hardware and we're seeing a signal from that hardware. And you can see the signal that we see here is kind of a low frequency background noise, a background signal. Low frequency sine wave, and then every now and then you have this burst, a high frequency burst. So you have a high frequency component that shows up randomly every now and then. And so what I'm going to show you guys is an example Python script where we take this data as an input, and then we use the facilities in Python to detect the regions where you have a high frequency burst. So I'll stop this for now, and I'm going to open up so this is the LabVIEW end of the program, and there's a corresponding Python program that runs alongside it, which is here. And I can open that in Canopy. And so just in the same way that the Hello World program had, a LabVIEW component and say hello.py, this program has got a LabVIEW component that you just saw, and this is the Python component that we're going to use to do the heavy lifting for the signal analysis. And so the idea here is that there's a Python function, and it's much more complicated than the say hello function we had before, but it's just a Python function called find bursts, right? And it takes as arguments, it takes the signal, which is an array of numbers that represent the signal, and a whole bunch of optional arguments that control things like the sampling frequency, the threshold above which you would like to detect these bursts, and some parameters that affect how the algorithm works, to do smoothing and so forth. And way down at the bottom, this thing is going to return a two-dimensional array. That's a list of the regions where we think we found frequency bursts inside the signal. And so I won't bore you with the math in the middle over here, but I will direct your attention to the top of this file. This is kind of the most important thing in the file. This is a very common thing you're going to see in the Python world. At the very top of the program, we're going to import a series of packages. And the two that we're importing are called SciPy and NumPy, and these are kind of the standard tools that you use in the Python world for doing numerical things, for doing array or operations, for doing signal processing, and so forth. And in particular, SciPy, which is this huge toolbox of functions that do interesting things to signals. And so we're going to use a few functions from that. But these are not, this, for example, does not ship with Python. This has to be installed. And one of the benefits of using a real Python environment like this is that it comes with a package manager, right? And so if I wanted to install SciPy and have access to all this great functionality, right, I launch my package manager, and now I've got access to all this great stuff, right? There's over almost 500 packages that are available to be installed. And if I want any one of these things, right, I just click this install button, it installs it, and it shows up in Python, I can start using it. So we're going to import SciPy and NumPy and do the heavy lifting here. And of course, it's just talk to compile the C libraries. So it's very efficient. We have our thin layer up here of Python code that does the coordination, that does the glue to solve our problem. And so I'm going to close out of this right now and go back to our LabVIEW program. And I'm going to look inside this, the block diagram, substantially more complicated than our hello world example. But the important part is right here, right? We do the same kind of pattern. We have a new session.vi. We pointed at this frequency burst.py module. We asked it to hide the console, so we don't have to see the Python console. And then we have a loop here where we're acquiring signals. And the acquired signal was packed to be sent as an argument to our Python function. We also provide some of these optional parameters, the sampling frequency and the threshold above which we want to find the bursts. We call the find bursts function. We retrieve the data from Python. And then we unpack it, and we unpack it into this two-dimensional array that gives us a list of these regions in the input signal where we think there's a burst. I'm going to go back to my front panel here. I'm going to set my frequency threshold to something more reasonable, like 150. And now when I run the program, Python will be running in a separate process alongside LabVIEW, and we're going to exchange this data. We're going to send the signal every iteration. We're going to send this signal over to Python. It's going to run the script, this analysis, and going to figure out where the regions are, and it's going to return it back to me. It's going to display it here in this array, regions found by Python, and it's going to highlight in the signal box over here where it thinks the regions are. So I'll run that. And now you can see it's totally seamless, right? Python is running alongside, and every time you call this, you get a list of the regions. And so these are the raw regions. It parts on the x-axis where it thinks is a frequency burst, and in red you can see the highlighted regions over here. So this is an example of what you can do with Python to do live processing of time series data. So that's an example of time series. But of course, the toolkit and Python itself can be used for much more than just signal processing. I'm going to close out of this demo. And the next demo I want to show you guys from our demo suite over here. One of the important applications for LabVIEW for sure, and increasingly for Python, is being able to process images. And so there's a wonderful toolkit in the open source world called OpenCV, which provides a whole series of Python bindings that allow you to call it from Python. And OpenCV is, the CV stands for computer vision. And the purpose of OpenCV is to provide this huge library of functions that are useful for doing image recognition, for doing signal processing of images, histogram normalization, and so forth. And so the demo that I'm going to show you guys here is the LabVIEW program. This could take data from a webcam, for example. We're actually going to read data just from files on disk. It's going to display the files in this view over here, the images in this view over here, and we're going to use OpenCV through Python to do detection of human faces in the image. This is one of the standard demos that you can actually do with OpenCV out of the box. It comes with facilities for doing detection of objects, including faces, out of the box. And so this is the LabVIEW end of the system over here that acquires the image data. And if we go over here to our examples, face.py is a corresponding Python side of the connection. And just in the same way that we imported the NumPy and SciPy packages, here we're going to import OpenCV. And so at the top of the file, you get some imports. Here's NumPy again, and some things in the standard library in Python. And you've got CV2, right? And so I import CV2, and now I have access to this huge library of functions that are written in C and C++ and can do whatever I want. And in the same way that we had a function for say hello and we had a function for doing the region detection, we got a function here in Python for finding faces in the image. So this function takes an image. This is an array, a three-dimensional array, so height by width by the number of colors, right? It takes a series of collection of optional arguments that control how the face fitting happens. And then it's going to draw the rectangles on this image where it thinks the faces are, and it's going to return the entire image to LabVIEW as a three-dimensional array. Pretty straightforward. And this is actually pretty short. I mean, something that does some sophisticated math like finding faces in an image, right? This is like 20 lines long. So there's not much in here. Again, because we're leveraging this wonderful universe of software that's available in the Python ecosystem. So here's my Python end of the bridge. I'm going to minimize that. And in the same way that we ran Python, in a hidden console in the background in the previous demo, we're going to run it in the background for this demo. I'll run the program. It's going to load an image. This is a picture taken from one of our conferences. We had a conference here in Austin in July, and so we took this photograph at one of the sprints. And so you can see here, this is the image from LabVIEW, and it's being passed off to Python, and then Python is finding the faces and then drawing boxes where it thinks the faces are. And so Python, in the same way that we had available to be run in the background in the signal example, is running there live, and in response to changes here, right, I can change the parameters, optional parameters in Python, and it will recompute the face fit and then display it again here in LabVIEW. And so if I close out of this and go to the block diagram, right, there's a whole bunch of fancy stuff in here from LabVIEW so they can respond to the mouse clicks and so forth. But at its heart, it's the same thing. You've got a new session, right? We're talking this face.py script, and now instead of sending a signal across to Python, we're sending our optional parameters like neighbors and the scale factor, and then we're sending a three-dimensional array. And you'll notice that sending a three-dimensional array to Python is as simple as it is to send a string or a one-dimensional array. Right? We do all the data, the type conversion, and so forth automatically. And it's very easy. You can return a three-dimensional array from LabVIEW to Python to LabVIEW in a very straightforward fashion as well. And here it is. We unpack it and we display it with the green rectangles. We display it on the front panel of the VI. So that's OpenCV. And the next thing that I want to talk about here, it's very exciting. One of the great things about the Python ecosystem, like I said, it's a larger ecosystem than just us folks in science and engineering, right? And so one of the benefits of that is that not only do you get these general purpose stuff like, for web development and so on, but when folks produce a cloud service, like Amazon or Azure or the Plotly folks, you actually get typically a Python interface. And so any of these services that have got a Python interface, you can now talk to them from LabVIEW. And the example that we're going to show you guys here is using a cloud service called Plotly. Plotly is an amazing service that allows you to basically make and share graphs on the web. And so if you've got some data in LabVIEW or in Python or in MATLAB or whatever that you want to share, you typically right now you would make a plot in that environment or in R or whatever. Right? You make a plot in that environment, you save it as an image file, and then you email it to somebody, right? And so the idea behind Plotly is it's a web service running out there in the cloud, and you can make your plot, you can provide the data for your plot, and instead of showing up in a window on your desktop, it shows up on the web, right? And so it talks over HTTP, and it's very fancy. So what we're going to show you here is how to use the Plotly Python interface from LabVIEW to accomplish this kind of remote plotting. So I'll go over here to my example suite. And again, this ships with the toolkit, so you guys can get your hands on it. And it's called Publish Data to the Web with Plotly. So this is a simple LabVIEW VI. It's got just some static data over here. But again, you could take this data from an instrument or from whatever, like the same way we did, in the previous signal processing demo. And the Python side of this connection over here, it's called plotlybridge.py. I'll open that. And in the same way that we imported OpenCV or we imported SciPy or NumPy or any other Python packages that we've been using, we're going to import Plotly. So import plotly.plotly as py. And there's a function over here which is very short. This is our bridge between LabVIEW and the Plotly web services, right, called post to Plotly. And you provide the data you want to plot, and you provide a name you want to have for the plot, right? And then it calls the Plotly API, and it hands it off to the web server. And so it's very straightforward. And so there's not much in here, right? There's an adapter function we wrote that just takes your data and then calls the Plotly Python backend. I'll close out of here. Back to our main VI over here, and on the block diagram, right? One of these things over here, I push the send to Plotly button, and it's going to just pack up my data from the front panel. It's going to give it a name, my plot, and then it's going to call post to Plotly. Go over here, and Plotly, by the way, by default, when you call that, Plotly is going to try to open a web browser so that we can see our data on the web. So I'll run it, and now it's just waiting for my input over here. I'll push the button and trigger off that event case. and it's going to take this thing over here, right? And so now it's sending the data off to the cloud, off to the Plotly web server. And if you want to, you can also provide information like the titles and the layout and so on. I kept it pretty simple for this demo. And here we now in our plot.ly under my user account. Here's the graph that we had. And this can be shared with folks, and it can be modified. You can make it make it look nicer or whatever you want to do. So with almost zero effort over here, we took the advantage of the existing Python Plotly bridge that already exists, the Plotly package that already exists, and got access to our cloud service directly from LabVIEW. Now, one other demo I want to show you here for Plotly that kind of shows off the things that you can do by composing these open source packages is that not only can you post data from here to the Plotly web server, you can also run in Python a local web server right alongside LabVIEW, right, and exchange data back and forth live. And so here is the demo VI for that, live Python-powered web dashboard, right? And so this uses Python in kind of a different way than we've been using Python in the previous examples, right? The previous examples, you have a function that does something interesting. You start up in LabVIEW, you call the function a couple of times, and it does some processing for you. The idea behind this VI is that when you can launch a Python web server in that process that runs right alongside LabVIEW, and you can exchange data. You can pipe data from LabVIEW to Python and display it on the web. So I'll run this. And just in the same way that we had in the signal processing example, we had data coming in from hardware, we now have some fake data coming in, from this VI, and it updates about once a second, right? And there's a button here, Launch Python Dashboard. This is going to call to a Python script, which is going to launch a web server in a separate thread. And now, it's called LabVIEW Dashboard over here. Now, every time we get data coming into LabVIEW, we can send it over this bridge from Python, and it can be displayed on the dashboard. And so this is a way, it's kind of showing off in a way, but it does provide something very useful, which is that you can use these Python facilities not only for plotting, but also for using web servers and web services to build these small apps that can run in the web browser or wherever you want them to run. So that's an example of the kind of things you can do by composing these open source software packages together into a solution. Now that we've gone through our suite of examples over here, the last thing I want to show you guys very briefly is this thing called Application Builder. And so for folks who may not have used these facilities in LabVIEW, is this wonderful tool that ships alongside LabVIEW. And so you have your LabVIEW program over here, right? Suppose I wrote this program, and I wanted to run it on a different computer, right? This is running inside the LabVIEW development environment. I got LabVIEW installed on my computer. I got all the libraries for LabVIEW, and it's running inside of LabVIEW. But there is a tool that ships along with LabVIEW that allows you to take this program and bundle it up and distribute it into an ordinary Windows installer so that you can install and run this LabVIEW program on any Windows computer. And this is really useful, as you can imagine. And so we are working. One of the problems with that, right now, is that of course if you wanted to use Python, right? Your Python toolkit talks to this existing Canopy install where you've got your nice editor and all these things that are appropriate for development, right? And so your LabVIEW, it assumes that you have Python available on the system to be accessed from LabVIEW. But of course, if you make use Application Builder to build a distribution and you deploy it on a different computer, then you don't automatically get access to Python. And so we are working on a tool that will ship in the next minor release of the toolkit, which allows you to take your Python code, like this code right here, along with all the dependencies, right? Like Plotly, like NumPy, like SciPy, like OpenCV, and bundle it up together in a way that is very, very easy to distribute alongside Modular, right? So I'll show you guys this tool, close out on my example here. So this is pre-release. This will be in the next minor release of the toolkit. So as a menu item under the tools menu that we provide with the toolkit, and one of these options here is export Python runtime. Click on that. It's going to figure out where your Python is. It's going to ask you for an output folder, and now it's going to look at that Python installation. Here is the list of all the Python packages that are installed in that Python environment, right? I got OpenCV over here if I want to include that, right? I can include SciPy down here. And so you can pick and choose which packages you want, and it will collect these along with all their dependencies into a standalone Python runtime. And so the end result is that you can build a LabVIEW application powered by Python that you can then distribute and will run very easily on a different computer. And so, for example, here's one that we've already built. when you run Application Builder, here's the input, for example. There's our app that we're going to run. And this is a simple project. It's got one VI. This is running under LabVIEW right now. This is main.vi. It's basically Hello World, right? You run the thing, and just in the same way we did the Hello World demo, right? You put your name in here. And this is under LabVIEW, and it's calling out to Python to do this transformation from the string to the output string. And so in this project over here, you can add a build spec, and you can do a standalone application and an installer for that. And when you include the output from that Python tool that I showed you, the result is that you get this installer, standalone Windows installer, right? You run that. So this is coming from Application Builder, right? This is a thing built into the LabVIEW. It's a standalone installer. You can install that little application that I showed you, the Hello World application. Under Program Files, it's a real Windows application. You run that. And now, of course, I got LabVIEW on my computer, but if I didn't, then of course it would install the standalone LabVIEW runtime. Totally transparent, very easy to use. It's running, and it's done. And now, as a post-install step, it's going to expand a standalone Python environment in Program Files, in the application directory, that is totally unique and private to this program. And so it's got its own copy of Python and all the libraries that I wanted to pick. And now, in Start menu, here's your application. This is now running on its own, and now it's using its private copy of Python to accomplish this transformation. I put a name in here, right? It's using its own copy of Python to accomplish that. And so I can do image processing, machine learning, signal processing, whatever I want to do, totally isolated from everything else in the system. All right, well, that concludes the live demo portion for you guys. We didn't want to put too much in there, so I hope it was useful. The last thing I'm going to show here. So this is kind of a summary of how you get your toolkit, how you get the toolkit, and so forth. We are shipping the standard way for shipping add-ons in LabVIEW is through the LabVIEW Tools Network, and we are on LabVIEW Tools Network. You can go to this web address at enthought.com to get a link to the LabVIEW Tools Network download page. If you know what a VIPM is, you can also install it through VIPM. The toolkit ships is a fully functional 30-day trial that includes not only the toolkit but also a full installation, if you want, of Enthought Canopy. Support LabVIEW 2015 and later, Windows 7 and later. And like I said, it includes Enthought Canopy, and it can also use your own Python if you want to. Basically, any CPython 2.7 distribution will be fine. Some details on how the licensing works. We want this to be as easy as possible for you guys to use, and so we are using the standard approach used by LabVIEW and by Enthought Canopy, which is a named user license. And so you buy it, it belongs to you, and you can use it on up to 3 computers. We are including a 1-year license along with that purchase for Enthought Canopy. That means the advanced features, including a debugger and data import tool, ordinarily sells for $200. And the sticker price for the integration toolkit is $749. And if you're interested in academic pricing and volume discounts, please do contact us. Those are available. Okay, I guess you guys have been keeping Courtney and Jim busy, and so we have a minute or two here for questions and Q&A. So what do folks want to know?
I have one question from Martin, who wants to know if it's possible to call LabVIEW from Python.
Awesome question, yeah. So there are actually existing tools that you can do for that. So a couple different options for that. National Instruments, an NI employee does maintain a GitHub project for kind of LabVIEW automation, which is very useful. I recommend you check that out. There was a talk at that at NI Week this past month that you can Google for to see that. If you do want to use the toolkit, you can have two-way communication. And so in the same way that I showed you guys running a web server, if you have LabVIEW and Python already running, you can actually do two-way communication. But please do check out that NI project. It's very useful. I believe it's called the Python Automation Library.
Another question. Do we have any benchmarking for the communication between Python and LabVIEW?
Awesome question. Yeah. So one of the important things for this, I showed you guys examples where you do processing of images and signals. And one of the most important things to us was that this connection be as efficient as possible, right? And so the communication between LabVIEW and Python is based on a very efficient binary protocol. We're doing almost no data conversion. It is no text involved. We're not flattening to JSON or to XML or anything like that, right? This is real numerical data. And so we were able to very efficiently send things like images and numerical arrays back and forth. I think the benchmarks that I did just a few weeks ago, we're seeing speeds in excess of 300 to 400 megabytes a second to go from LabVIEW to Python, and also latency is in the millisecond range. So very efficient. Great. Okay. Well, I don't want to keep you guys here longer than we have to. It's about the end of the session here. I think it's 45 minutes past the hour. So if there's nothing else, thank you guys for your attention, and we look forward to talking to you. All right.